Great. Yeah. Nice. Okay, let's start. Uh, almost last week, week 9. So today's plan is to focus on mean field theory. So here is the content. First, I would like to very briefly mention the exact solution in 1D and 2D. I know you learned how to solve for the Ising model. How to solve the Ising model in 1D. And in 2D, I will briefly mention it. And then, okay, let's apply I know the professor also did this in the class, but I think it's kind of good to compare those two when like the mean field theory for applied to this Eisen. The second part I would like to say is apply this mean field theory to a quantum model, which is known as the transverse field Eisen model. Transverse field Eisen model. And then I will kind of introduce also very briefly mention this mean field theory in the second quantization notation. And then the last point I want to say, definitely for every theory, we should ask ourselves when it will break down. Breakdown of mean field theory. And usually after this breakdown of the mean field theory, we will introduce the notion of RG, renormalization group. Yeah, that's the plan. And also feel free to stop me whenever you want. So for the Eisen model, I mean, this is always the model we used to kind of illustrate the idea of mean field, right? Because it's simple. In 1D and 2D, there are exact solutions. And in 3D, 4D, there's no exact solutions, but usually people do it numerically. And there's no phase transition in 1D. And I think we discussed it in kind of in previous discussion section. It's like a very simple argument, because at all temperatures, the domain all will proliferate and destroy the orders. So it's always a disordered state. There's no order. Basically no spontaneously symmetry breaking in this system, right? And if you calculate the free energy, I mean, here I just kind of saying stuff that you already know, but I think it's good to kind of refresh your memory about this. If you calculate the free energy that you calculate in the class, which is minus epsilon, by the way, let's set the Hamiltonian to be this log something. The argument here is 1 plus exponential minus 4 epsilon divided by t. Hope I'm not making any typo, right? I mean, from this free energy, we immediately know there's no phase transition, because this free energy is smooth anywhere, right? To have a phase transition, we want the thermodynamic function to have some singularities or discontinuity at some point, right? And you may wonder that anyway, the starting point is a partition function, which is a trace of some exponential, so basically it's beta E1 plus exponential beta E2 plus So every term is, oops. Can you guys hear me? Okay. Yeah, every term is smooth. So to get a singular result, we must require the system to be infinite. That tells us to have phase transition. So basically phase transition can only happen in the thermodynamic limit. That's the conclusion we can draw from kind of a simple argument. Okay, so in 2D, this is 1D and everyone familiar with this. And in 2D, this is a general argument, comment. So in 2D, the solution is first presented by a paper by Onsager. So let me write down this paper. But no one ever really read through this paper, I think. Because it's very complicated. And the language is not modern language. This guy used quaternions and this kind of old-fashioned language to solve this problem. It's totally unreadable. Later on, another guy, let me read. Usually people read this paper. Another guy, I think they talk to each other, and this guy rewrite, kind of translate this paper into a modern language using polymetrics. We know that quaternion and the polymetrics is their correspondence. There is a correspondence, right? The algebra are the same. Yeah. Right. Yeah, this one is readable. Basically solve this 2D Eisen model using the representation of SO, SON, S2N. N is the size of the system. Yeah, and if you look up on this kind of papers, you would find they figure out the free energy for this Eisen model in 2D, which is given by, this is the exact result. There's no approximation. Some log function. Okay. I'm not deriving anything, I just write it down. This beta is the standard 1/t, kBt. And plus there is an integration, the phi is some variable. 1 minus that square sine. Something like this. Okay, this phi, sorry, this delta, okay, looks very complicated, but okay, I just write it down for you guys, but you don't need to remember what's this expression, you just need to, there's an exact solution, and for completeness, let me write it down. I mean, you may say, okay, this is also not obvious. There is a singularity. From this, we know we can calculate the energy and also the CV, the heat capacity. From this guy, you can say, indeed, there is a singularity, which is very obvious. Let me write it down. Everything is exact. There's no approximation. Right. If you draw the picture for the CV, this is a T. There is a special point TC at which the CV is divergent. And this TC is fixed by setting delta equal to 1, and is given by 2 epsilon log square root of 2 plus 1. Yeah. That's the rigorous solution for the 2D Eisen model. And just a side remark, actually, people without solving it exactly, people can determine the critical temperature. That's because at no temperature, we can do kind of a perturbation to calculate the partition function. And at high temperature, we can also somehow do approximation to calculate the partition function. And the people realize that those two partition functions are related to each other. Imagine this is beta. Beta is, is 1 over temperature. This one is another beta tilde. They related with each other. There are some numeric factors. We really don't care. So beta, they are related by, let's see, sine, sinh beta equal to 1 over sinh 2 beta epsilon. So you can say if beta is larger, then beta tilde will be smaller. That means if I know the temperature at beta tilde, for example, let's say at low temperature, then we will get a partition function at high temperature. So this just tells us, this is, by the way, this is called Kramers. I think something like this. There's no 1M, I think. Kramers 1 year. Yeah, duality. So there are many theories in physics. They look different, but they actually can be mapped onto each other. That's what we call duality, right? And there's a special point that is when those two temperatures are the same. So basically, setting beta tilde equal to beta corresponding to a self-duality point. And then if you solve this equation, you would get this temperature without kind of involving so kind of complicated calculation. People figured it out. Yeah, it's very nice. Okay, that's some side remarks about 2D Eisen model. So another thing is, another side remark about 2D Eisen is, to say there indeed a phase transition, one can calculate, the mechanization as a function of T. And this work, by the way, for this partition function in these two works, they calculate the partition function without magnetic field. And with the magnetic field, the result is given by this guy. This is also a famous guy. Yang is the same Yang as in the Yang-Mills field. It's also a very old paper. It's given by 0, above the critical temperature, and some, by the way, this is also an exact result. Whenever there are some exact solutions, for many body system is always amazing. T smaller than TC. And if you draw the picture, TC, let's say this is a TC, this is M, it would look like something like this. Yeah. That's basically all the conclusions about two-dimensional Eisen model. Yeah. Okay, so I mean, there's a people always care about the critical exponents, right? For this kind of at the phase transition point. For this phase transition in 2D Eisen model, M is proportional to, but you can expand this guy around the TC and you will find TC minus T. The power is 1/8. I mean, it's this guy. There's no, it's not surprising, right? And by the way, in 3D, numeric results shows M is about 0. How much? 32, I think. Yeah. Yeah, that's the exact results. And now let's solve this problem using mean field theory. Since you already kind of the professor already did this in the class, so I will very briefly mention it. So let's say some general stuff about the mean field theory. By the way, any questions so far? Okay, sure. So I mean, for the mean field theory, basically we replace the actual configurations of local variables by their average values, right? We neglect the fluctuations and only kind of reduce the interactions problem to a free problem. That's basically what we did in mean field theory. So first thing is if there are more spins interacting with a particular spin, then for that particular spin, it's say kind of it's a more this particular spin say an effective average field. In that sense, we can say in higher dimension, mean field theory becomes a better approximation, right? And as you will see, when we discuss the breakdown of mean fields, there is a critical dimension which is 4. Above the 4 dimension, the mean field theory is always good. Is a good approximation, and one can actually argue that when d goes to infinity, the dimension goes to infinity, the mean field theory is exact. At lower dimension, like below 4 dimension, like 3 to 1 dimension, mean field theory always breaks down near the critical point. And there are some, yeah, as we will see. And in that situation, we need to introduce the, the groups, renormalization group to get the critical exponents and stuff like that. Yeah, one is basically, dimension is higher, we have a better result. And the second thing, for the mean field theory, we basically reduce interacting problem to an interaction-free system. right? To say that, there's one thing I want to point out in the mean field for the Eisen model, which is there's an interaction term Si dot Sj, right? And so how will we apply the mean field theory? We need to kind of decompose my S, the variable, into two parts. One part is the average value, another part is a fluctuation, which is Si minus M. This part we denote as delta Si. So this term becomes M plus delta Si times M plus delta Sj, which is M squared plus M delta Si plus delta Sj plus delta Si delta Sj. And if you plug in this, you would get M Si plus Sj minus M squared plus delta Si delta Sj. So far, everything is exact. We didn't make any approximation. We only separate, our variables into the kind of the, the average value and also the fluctuation around the average. The mean field approximation says we can ignore this last term. That's the only approximation we made in the whole problem. And then this interaction problem becomes free problem, interaction free problem. There's no interaction. So as you can imagine that when will the mean field breaks down? It will break down when this fluctuation is comparable or larger compared with the mean value, right? At that point, it makes no sense to say, okay, this is a mean value, this is a fluctuation, because they're already comparable. Is it clear so far? Yeah, great. Right. And after the mean field calculation for the Eisen model you did in the class, we would get T C minus T. This exponent, critical exponent is 1/2. As you can see, this guy is approximately, sorry, it's exactly this number. So you can say as dimension goes higher, it's approaching this 1/2. Yeah, that's the one observation. Okay. Yeah, that's the kind of a review of this Eisen model mean field theory. By the way, another comment, this mean field theory in terms of path integral is equivalent to say is equivalent to the saddle point approximation. We only keep the lowest order of this approximation. For example, okay, let's say I have some theory of some variables, let's say M. Because it's an interacting system, meaning that there must be some M squared plus M cubed, something like that. If we have only M squared, then it's a free problem because it's Gaussian integral. Gaussian integral, we can always do it. And this mean field theory just tells us we only need to calculate, let's say this guy is Fm, delta Fm. There's a particular value M naught and plug in. That's our partition function. That's it. And on top of this, of course, we can calculate the fluctuation. We can expand this function, using by setting M equal to M naught plus delta M. And then there will be del m square, and we can calculate the fluctuation and compare this fluctuation with the mean value. That's how we get the critical dimension. So here I'm not really deriving anything, I just kind of sketch the idea that you will learn in STEMAC-B. There's I don't know whether the STEMAC-B class will be there next year. I don't know. I remember when I was in like first year, there is a STEMAC-B, but at that time I was taking so many other classes, so there's a confliction. So from after my first year, there's no longer STEMAC-B. Yeah, but anyway, you can learn by yourself. There are many online courses. Okay, that's the Eisen model. Okay, another comment. So for the in the 3D Eisen model is in the same universality class with the liquid gas transition, meaning that at the phase transition, they can describe it by the same theory. That's the in the same universality class with the liquid gas transition. I mean, many physicists believe that the goal of condensed matter physics is to find all the fixed points. Because, you know, that's why the renormalization group plays an important role in modern condensed matter physics. Okay, so let's talk about the quantum model. So if I ask you to construct the most simplest non-trivial quantum model, how would we start? Okay, first, I would assume the system is translational invariant. Basically, on each point, on each side, kind of they're identical, right? Second, I would assume the Hilbert space on each side is very simple. For example, there only the Hilbert dimension is 2 dimension, basically 2 levels. Then that means you have a spin, right? Sigma z, for example, some spin on each side, spin 1/2. Now, to make it non-trivial, I want them to be interacting with each other, right? Then we have sigma z I and sigma j z, something like that. But this model is equivalent to the classical Eisen model, right? Because it's just a diagonal elements. There's no off diagonal elements. There's no quantum information. So in that sense, we would like to make this model quantum. We only need to add the extra term that's not commuting with sigma z, which is, for example, sigma x. Then you would say classically the one spin is kind of a staying up, which is 1, 0, but this term does not commute with sigma z, meaning that this sigma x will mix your up-down state. So there's a competition between those two terms. By the way, we're discussing zero temperature, meaning that the phase transition here we will talk about is a quantum phase transition, happens at 0 temperature. Right? This model is so-called the transverse field Eisen model. You can say this looks like a transverse field applied in the x direction. this part is kind of Eisen model. That's why people call it transverse field Eisen model. And this is the most simplest model we have. And so whenever people have some ideas, new ideas, they usually try it on this model. Nowadays, there's a one very hot topic is non-Hermitian system. When the system is coupled with some open quantum system, where when people are doing measurement on the system will, the Hamiltonian will be non-Hermitian. And the people also try this kind of idea on this models, and there are several papers this year on this. And another comment about this model is important because by a Jordan-Wigner transformation, you can map this model onto a fermion model and can be solved exactly. This model mapped onto a free fermion model. And for the on that fermion model, for fermions, just like the boson operator, A dagger plus A equal to X, A dagger minus A equal to P, you may wonder if A is not a boson but fermion model, a fermion operator, what this guy is and what this guy is. It's just nothing but Majorana fermions, and that's also connect to another story. So that's why this model is kind of interesting. Yeah, some very lot of comments, but let's back to our story. So we want to solve this problem using mean field theory. How would I start with? Like, what should I do as the first step? Okay. Let me introduce some coupling, like the coefficients. I still assuming it's a ferromagnet, and for the anti-ferro, you can do similar analysis. I introduce a length scale, kind of a dimensionless variable, parameter G. Then this theory is totally controlled by this parameter G, right? I mean, before any calculation, we can look at two limiting case. G equal to 0. In this situation, we have only this term, the first term. Then the ground state is up, 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 or down, down, down state. When G goes to infinity, the second term dominates, and the eigenstate, the ground state would be this state. This is defined by the eigenstate of sigma x, right? And in some sense, if you want to do the analogy with the Eisen model, this can be thought as the ordered state. And this can be thought as a disordered state. And you can imagine that there must be some phase transition at some value, right? GC.
Hey, G, so what do you mean by disordered state? Like it's not periodic system, or? Okay,
so disorder, I mean, the symmetry is not spontaneously breaking. Just like the ferromagnets, you have this kind of a rotational symmetry. In the disordered states, the M is 0, meaning that I'm not choosing some particular direction. But in the ordered states, the ground state is always pointing in some direction, right? Yeah. Then in that sense, or for example, in ordered state, you have infinite many ground states because you can point in any directions, right? That's why you have some Goldstone modes like magnons in ferromagnets and the phonons in the kind of a lattice, right? And here in the same spirit, like yeah, in that sense, yeah. Okay, thanks for asking. Okay, so for the mean field, so okay, mean field. Let's look at the mean field phase diagram. Okay, so even though the mean field approach looks very simple, but people always use it to, whenever you have some new theory, new Hamiltonian, you can always ask what is the mean field phase diagram. Even though sometimes it's wrong, but usually it can give you some intuition and before you start digging into more detailed analysis. So just like what we did before, okay, the essence of this mean field approach is like treating regarding, reduce this interacting problem to a free problem, right? So if we have a free problem, meaning that on each spins on each side will be no interacting, there will be no interaction, right? That means there will be no entanglement between spins. So in the spirit of this mean field theory, it's reasonable to assume the ground state is a tensor product state. And okay, so what this state is, in generally speaking, the most general form is just an arbitrary state on the Bloch sphere, right? And we can parameterize it using theta and phi. There are only two variables, free variables for the state on the Bloch sphere. So here you can use up and down, but for convenience, here we use the right and left. And we can apply this. Okay, we can calculate energy as a function of theta and phi for this ground state. It's very simple. Just apply phi to h, and as you can see, because we assume it's a product state, then there's no interaction anymore. For example, for this term, iz sigma jz, there's some other terms. I just show you, of course, we're running out of time. So, I, sigma I, they, remember they are on different sides. So it's just I. Okay. Okay. Right. And we can calculate this very easily. In general, if it's an entangled state, meaning that ij, there's no way to kind of decompose my wave function into two parts, then we cannot do this, right? And also this is known as the mean field trial state. And after calculation, I mean, this is easy because just basically sigma z acting on this. And the sigma, there's another term sigma x. Sigma x acting on this, we know how to do it. And let me write down. The final result is minus n. N is the total size of the system. That's the ground state. Of course, we want to minimize the ground state according to the variational methods we learned in quantum mechanics to reach the real ground state. So we immediately see that the phi must be 0 or pi, right? Recall the range for theta is from 0 to pi, and the phi is from 0 to 2 pi. Now, how about the value of the theta? Then that's okay. The value of theta when phi equal to 0 or pi, this guy becomes 1, right? Let's look at this guy in past what this is. So this guy translates into, I mean, you just take a derivative. There's no fancy calculation. Becomes sine theta times 2 cosine theta minus g equal to 0. So there, in generally speaking, there are 3 solutions. One is sine theta equal to 0, meaning that theta equal to 0, and another one is cosine theta equal to g divided by 2. And there are 2 solutions for the theta. However, when g is larger than 2, this guy has no solution. There's only one solution, theta equal to 0, right? So when theta equal to 0, as you can see, what is this state? Theta equal to 0 corresponding to this term goes away, and this only left with this guy. So indeed, this is what we have. This agrees with our intuition. So basically, there's a critical point, which is GC equal to 2. Above this point, the ground state looks like this. And below this critical point, if you draw the picture for the E theta, the one looks like this. And this is theta, this is E theta. This corresponding to theta equals, even though theta equals 0 is a solution, but it's an unstable solution. And we have only 2 solutions. That would give us the 2 state below the GC. That, I mean, in general speaking, it's not just up, 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 down, down, down. It's some specific value of theta, theta naught. It's theta naught equal to arc cosine g divided by 2. However, when g goes to 0, g goes to 0, cosine theta equal to 0, meaning that theta equal to theta equal to pi over 2, and the phi is 0 or pi. Those two states correspond to up, up, and down, down, down. This gives us what we have before. Yeah, this is a very kind of a simple analysis for this quantum model, but we can get some information and obtain this critical point. Yeah, that's I want to say about this transverse field as a model. I think we are running out of time, so okay, let me very briefly mention the breakdown. But if you can go if you want. You're free to go. But I just want. Anyway, I will upload my notes on the CCLE, so you can take a look. There's a mean field theory in the second quantization notation, and one could the very well-known Hartree-Fock approximation, and also the Hartree-Fock, and also the what's the name? Oh yeah, superconductivity, or just BCS theory. One can reproduce this kind of theory in the mean field theory. Basically, okay. So if you it should only takes 1 minute or so, and let me state it. So basically, imagine you have some state C dagger CC. This is an interacting term, right? And the mean field tells us we need to introduce some fluctuation field. And say is the F, which is C dagger C. By the way, this can be written as C dagger C, C dagger C. There may be some indices, right? Mu prime. I really don't care necessarily to know the indices. The idea is like this: C dagger C and minus the average. That means C dagger C can be written as delta F. F is also operator, remember? And you plug in. Then this term would give us C dagger C times the average plus C dagger C minus C dagger C, C dagger C. Then this interacting problem becomes a free problem because it's quadratic in C, right? And we can calculate this C dagger C by using this mean field Hamiltonian. We would get a self-consistent equation for this C dagger C, just like what we did for the Eisen model, right? In the mean field Eisen Hamiltonian, we have the M, the mechanization. On the other hand, we can calculate the M using the mean field using this Hamiltonian. And this is the Hartree-Fock approximation for the BCS. You may notice that I have another way to introduce the fluctuation. That is the CC minus CC and C dagger minus C dagger. And usually people denote as delta. This is called the gap function of the superconductor. And eventually you will get a the BCS mean field Hamiltonian becomes some free part, the original free part plus originally C dagger CC. Now it becomes like a C dagger delta. Delta is this guy plus CC delta star, something like this. That's the mean field BCS Hamiltonian. And from here, you can do Bogoliubov transformation, stuff like that, get quasi particles, everything. Yeah, let me, okay, the last thing I want to say is a breakdown of mean field. So unlike what I said before, you can calculate the fluctuation of your field within, actually we calculate the fluctuation of the field within the correlation length. Yeah, and compare that with with the mean value, and the eventually, okay, so this is the fluctuation divided by some mean value. Eventually, we would get some divergent value of of a D minus 4 or something like that, divided by 2. Well, I didn't remember exactly. You can look up on the Carter's second book, the statistical field theory book, or another book, which is this one. It's the Principle of Condensed Matter Physics by Chalkin and Lubinsky. This book is also very famous. The chapter 5. Condensed matter physics. There's a book like, the title is this. Okay, so the D equal to 4 is very special. When D is larger than 4, it turns out mean field theory, this guy is always small. So mean field theory is good. When D is smaller than 4, it turns out, okay, this is T, some TC. Near TC, this guy becomes very large in some region. And we denote this critical temperature that as TG. G is the Ginzburg. We also call it a Ginzburg temperature. Basically beyond this Ginzburg temperature, mean field theory is still good, but within this region, it's not good. That's why at no dimensions, we always get the wrong exponents. That's kind of makes sense because mean field theory always breaks down at kind of a critical point at 3-dimension or 2-dimension level. Yeah, that's what I want to say. There's also an expression for this TG. Basically, it's TG minus T, their expression. We denote as small t, G. Yeah. And usually after this, people introduce the notion of RG and develop a theory for this kind of critical point and things like that. That's the structure of this story. Yeah, any questions? Okay, great. I'm actually not deriving anything, I'm just saying a lot of stuff. Yeah. Okay, great. Also, if you have any suggestion for the next discussion section, let me know. That will be the last one, I think, right? Great. If you have no questions, see you next week.
I guess we could just kind of overview everything for the last week.
Overview, yeah. If you want to, overview, yeah. I can do overview and give you some problems from my when I was taking this class with Suki. I have the final exam. I can show some problems. Great.
Okay.
Yeah, sure. Thanks for coming. Yeah. Bye. Nice.